Hello, thank you for your interest in optical coating technologies and OptoSigma. First, a quick introduction to optical coatings. They're used to increase or decrease the amount of light going through a lens or a window. As an example, without any AR coating, bare glass will lose about 4% of light per surface. Coating can be simple as a single layer of material or as complex as more than 100 layers of different materials. The materials are laid down in alternating layers of higher index and lower index to be able to provide the desired performance. What's referred to as thickness of a coating layer is actually optical thickness. It's the physical thickness multiplied by the index of refraction of the specific material at the specified wavelength, and are generally quarter wave or half wave thickness. Most simple anti-reflection coating is a single quarter wave optical thickness of magnesium fluoride or silicon dioxide, which reduces the reflection by roughly half. A half wave layer of these materials is commonly used to protect metal coatings from oxidation or other environmental degradation. When specifying or designing a coating, there are many details to consider which can greatly impact cost, schedule, and overall performance. For the substrate, the aspect ratio is important because stresses in a coating can cause the substrate to deform and drive the wavefront out of specification. There are ways to mitigate this, but it may come as a trade with performance. The surface quality of the substrate is also important because the optical coating will only be as good as the underlying surface. You cannot improve surface quality with an optical coating. Also, the clear aperture percentage and geometry will dictate how the part can be held in the coating chamber, and if the part has to be made oversized and edged or machined down to final dimension and geometry. The environment the part will be exposed to can also drive material choices in the coating layers to avoid delamination or degradation from crazing or discoloration or coefficient of thermal expansion mismatches. Additionally, different types of radiation can cause some materials to darken or disintegrate completely, and so they would have to be avoided. The overall optical design needs to be considered because the performance of a coating will change over angle of incidence, and if the lens has a very short radius of curvature, very steeply curved, and a large clear aperture, it can have a widely ranging performance across the clear aperture with all those angles. And so you may need to trade off performance again with the optical design. And if the specified glass type is soft compared to something like NBK7, it may require special handling or multi-stage coating to prevent etching by the ion or plasma gun in the chamber. Also, broadband coating is typically going to be more complex than a narrowband coating. And if out-of-band blocking is needed, then there may need to be performance trades made. Finally, from the system level, the wavelength of use may eliminate the use of certain materials in the design, and that can also have an impact on achievable performance. And that goes with laser power density as well. As laser power goes through your system, different elements will see different power densities as the beam is expanded and reduced, and could cause survivability issues with an optical coating. May dictate the use of oxides only, and that again may be a performance trade-off issue. Then there are also some materials that may not survive any given power density, and they would be avoided completely. And finally, polarization state or purity that you need in the system needs to be considered also to either maintain polarization or may not be an issue at all and you can ignore it. The process of getting to depositing material on a substrate is not as trivial as it may seem. There are many important steps. Ensuring the parts are extremely clean before they go into the chamber is critical to avoid chamber contamination, coating adhesion problems, coating print through from a small particle on the surface. And even the chamber itself has to be thoroughly cleaned, because if it has contamination in it, it may wind up contaminating the optical coating itself and cause failure. The materials to be deposited also have to be carefully loaded into the chamber, because you have to maintain the purity in order to ensure that your coating layer is exactly what you think it's going to be. The substrates have to be carefully loaded into planets, which are the metal discs that hold the parts and rotate to ensure uniform deposition. If the parts are not properly loaded, they could fall out as the chamber is heated because of the coefficient of thermal expansion, or if the parts move or fall out completely out, could cause failure or clear aperture failure for the parts. When the chamber is sealed and placed under vacuum, unwanted materials can outgas and contaminate the parts and chamber. And if the vacuum pumps are not properly maintained, they can leak oil or not properly maintain the necessary vacuum during the coating process, and it can again cause failure of the coating. Maintaining consistent temperature during the process is also critical for layer uniformity and proper adhesion. Finally, when everything is working as it should, the coating process begins. How long does the process take? Well, it all depends. There's things like the number of layers in the design, the thickness tolerance of the layers needed to obtain the desired performance. Higher performance and more complex designs will take longer. The size and quantity of substrates also impact processing time, because it's easier to obtain uniformity on smaller parts rather than one large part, so the rate can be adjusted to compensate for this. It also determines the number of coating runs needed to yield the final quantity of parts. OptoSigma's coating capabilities are generally split between Japan and the US. And in the US, we have over 100 recipes for coatings that are ready to go, already programmed into our coating chambers. So it makes turnaround quick. Where wavelength range of where we work, 248 nanometers, so UV, up to about 2.7 microns, 2700 nanometers. Our repertoire includes reflection and anti-reflection coatings for single wavelength to broadband or even multi-wavelength, and the ability to provide high laser damage threshold coatings. We can also reduce temperature down so it's at a lower temperature for deposition for those items that may require special handling that can't be exposed to the high temperature normally experienced in a coating chamber. And also our facility in California is ITAR registered for those type of projects. OptoSigma's parent company is Sigma Koki in Japan. In their facilities, we have much more extensive design and deposition capabilities, which allow us to offer the only commercially available super mirror with 99.999% reflectivity. We're also working on improving this even further to obtain 6 nines or 99.9999% reflectivity. Another specialty that we have is ultra-fast pulsed laser mirror coatings, such as our commercially available low and negative dispersion mirrors, where group delay dispersion is tightly controlled. Also unique is our extensive or extremely broadband beam splitter, mirror, and AR coatings that are generally designed to perform over hundreds of nanometers and designed for use UV to the near IR. We've also designed and manufactured many specialized coatings that we've been used in flight and space hardware application, such as the Mars rover Perseverance, which recently has been in the news. OptoSigma utilizes several coating methods at our various facilities. The basic process is electron beam or E-beam deposition, which deposits the anode coating material on pretty much everything in a line of sight. It goes everywhere. We also use amped up deposition processes that use either an ion assist or the even better plasma assist. Both of these methods result in a tighter packed molecules or atoms in the coating materials, with the most dense packing provided by the plasma source. The higher density decreases coating porosity, along with improved stability and durability. Some of the highest performance coatings are manufactured using IBS or ion beam sputtering, which originally was developed for telecom filters to yield high durability, high performance optical coatings. This method is used for the most stringent optical filter coatings. As the old saying goes, if you can't measure it, you can't make it. In order to verify performance has been met, you have to be able to measure the resulting coating with adequate metrology that tests it with the proper parameters and to the correct accuracy. OptoSigma has metrology to support all of our coating methods and capabilities, super mirrors, and also the GDD coatings. As you can see, all the pictures are a representation of some of the specialized equipment, including our cavity ring down spectroscopy ability. OptoSigma has coating capabilities in Japan, China, and the US to better serve our customers. Choice of facility depends on customer location, performance requirements, and cost target. Sigma Koki has been around for more than 44 years, and OptoSigma has been in California for 26 years and going strong. Our entire family has access to the full range of coating capabilities, and we serve customers in almost every industry and country. We welcome new challenges and continually work to improve our capabilities. This year, 2021, we will bring online the ability to coat substrates up to 1 meter in size. Thanks again for your interest in optical coating technologies and OptoSigma. Please get in touch with us. We'd love to work with you on your next project or quick turn optical coating needs. You can see on the bottom the different contacts in the US and Europe, and we'd be happy to work with you. Have a great day.